Welcome to the Peacademia course on the basics of semiconductors. This lecture covers the intrinsic semiconductors. Let's start. By the time you finish this lesson, you will learn the intrinsic semiconductors, intrinsic concentration, concentration of states in the conduction and valence bands in intrinsic semiconductors, and the energy gap, a function of temperature. One way in categorizing semiconductors was to divide semiconductors into direct and indirect. I covered this topic in the last lecture. There is another way to categorize semiconductors, and in this lecture and the following, I try to give a sense of that. We can divide semiconductors into intrinsic and extrinsic. In this lecture, I talk about the intrinsic semiconductors, and the next lecture will be about extrinsic semiconductors. Intrinsic semiconductors are those that are pure. In other words, all the atoms in an intrinsic semiconductor are identical. For example, intrinsic silicon is the one that all its atoms are silicon. We can discover some of the properties of intrinsic semiconductors through the energy band concept. At temperatures above 0 degrees Kelvin, a couple of covalent bonds are broken, and as a result, several free electrons and holes are generated. We already called this process generation. Let's show the concentration of holes by P and that of free electrons by N. In intrinsic semiconductors, the concentration of free electrons N equals the concentration of holes P. We call these concentrations the intrinsic concentration, and it is shown by N sub I. In intrinsic semiconductors, and often in extrinsic semiconductors, the occupation probability of states is much smaller than this concentration of states. We call these semiconductors non-degenerate. In non-degenerate semiconductors, the product of N and P, or Ni squared, is obtained by this equation. In this equation, N sub C is the concentration of states available in the conduction band. N sub V is the concentration of states available in the valence band. Eg, as you already know, is the energy gap, K is the Boltzmann constant, and T is temperature. For silicon, the concentration of states in the conduction band and the concentration of states in the valence band can be obtained using these two equations. As you can see, N sub C and N sub V are temperature dependent. Here again, we can see the equation to calculate the intrinsic concentration. Now that we have N sub C and N sub V equations, we can calculate the intrinsic concentration for the silicon at a given temperature. For example, at room temperature 300 degrees Kelvin, the silicon intrinsic concentration is 10 to the power of 10 per centimeter cube. We already know that the concentration of silicon atoms is 5 times 10 to the power of 22 per centimeter cube. If you compare this number with the intrinsic concentration, you'll find the concentration of atoms is 5,000 billion times larger than the intrinsic concentration. This is a huge difference. This diagram shows the intrinsic concentration temperature diagram not only for silicon but also for germanium, gallium arsenic, and 4H silicon carbide. What we can see immediately in this diagram is that the intrinsic concentration is highly dependent on the energy gap. For example, while at the room temperature, the silicon intrinsic concentration is 10 to the power of 10 per centimeter cube, the 4H silicon carbide intrinsic concentration is almost 0. This is because the intrinsic concentration response to the energy gap is exponential. The 4H silicon carbide energy gap is 2.87 times larger than that of silicon, and this creates such a big impact on the intrinsic concentration. Let's take a closer look at the energy gap dependency on the temperature. As I already said, by increasing temperature, the energy gap slightly shrinks. For silicon, the energy gap, a function of temperature, can be obtained using this equation. This equation says at 0 degrees Kelvin, the silicon energy gap is 1.17 electron volts, and for a temperature above 0, Eg gets smaller and smaller. At the room temperature 300 degrees Kelvin, E sub G for silicon is 1.12 electron volts. It turns out that we can generalize this equation to calculate other semiconductor energy gaps. Here is the general equation. In this equation, there are two constants, alpha and beta. These constants for silicon, gallium arsenide, for H silicon carbide, and gallium nitride are given in this table. You may need to spend a couple of minutes to go over all the information given in this table, so take your time, pause the video to have a better look at the contents of this table. In this lecture, I talked about the properties of intrinsic semiconductors, including the intrinsic concentration, concentration of states in the conduction and valence bands, and the energy gap. In the next lecture, I will focus on extrinsic or doped semiconductors. Thanks for joining this lecture of Peacademia.